climate change mitigation is a global priority, and carbon dioxide removal, CDR, is increasingly seen as essential for meeting ambitious climate targets. But as we scale up negative emissions technologies, a crucial question arises: how much land will these solutions actually require? In this video, we'll explore the area demand of different CDR portfolios, from biomass-based approaches to high-tech solutions like direct air capture. You'll see why understanding land use is critical, not just for climate, but for food security and biodiversity. Let's dive into the numbers and concepts shaping the future of negative emissions. The world has rallied around ambitious climate goals, limiting global warming to 1.5 degrees C or even 1.0 degrees C by 2100. Achieving these targets requires not only reducing emissions, but also removing vast amounts of CO2 from the atmosphere. Recent studies estimate that for a 1.5 degrees C target, we'll need to remove about 500 gigatons of CO2, while a 1.0 degrees C target could require up to 1,750 gigatons by the end of the century. These numbers are staggering, and they highlight the scale of the challenge ahead. But what do these targets mean for our land and resources? Not all CDR approaches are created equal. Some rely heavily on biomass, like bioenergy with carbon capture and sequestration, BCCS, while others focus on technical solutions such as direct air capture, DACCS. There are also hybrid options, including afforestation and biochar. Each portfolio has different implications for land use, energy demand, cost, and technology readiness. In this study, 6 portfolios were analyzed, each prioritizing factors like low cost, low energy, high security, low area demand, or high technology readiness. The choice of portfolio dramatically affects the area required for large-scale CDR. To truly understand land requirements, we need to distinguish between gross and net area demand. Gross area includes all land occupied or spaced out for technology. Think of the total footprint of wind farms, solar arrays, or crop fields. Net area, on the other hand, is the land that's actually consumed and unavailable for other uses, such as built-up areas or fields that no longer support biodiversity. For example, wind turbines require large spacing gross area, but the actual land they cover, net area, is much smaller. This distinction is key for assessing environmental impacts. Let's look at the numbers. For the 1.5 degrees C climate target, portfolios prioritizing biomass-based CDR can require up to 2.8 million square kilometers of net area, about 2.2% of the world's land. In contrast, technical portfolios relying on DACCS or similar solutions keep net area demand around 1% of global land. For the more ambitious 1.0 degrees C target, area demands rise, but the difference between portfolios remains. Biomass-heavy approaches need much more land than technical ones. The choice of CDR route has a profound impact on land use, with implications for food production and biodiversity. CDR routes can be grouped into 3 main types: biogenic, biotechnical, and technical. Biogenic options include natural afforestation, relying on photosynthesis. Biotechnical routes like BCCS and biochar combine biological and technical processes. Technical options, such as DACCS and enhanced weathering, are purely technological. Each type has unique area and energy demands. For example, biogenic and biotechnical options can require up to 9.7% of today's global cropland, while technical solutions have much lower land footprints but higher energy needs. Understanding these categories helps policymakers choose the right mix for sustainability. Integrating CDR into the broader energy system is essential. The study models not just the area for CDR technologies, but also the land needed for renewable energy sources like solar photovoltaics and wind power that supply the required energy. Interestingly, when the entire energy industry CDR system is considered, the additional area demand for renewables is relatively modest, especially for technical CDR portfolios. This means that, with smart planning, we can scale up negative emissions without overwhelming our land resources, provided we avoid over-reliance on biomass. Large-scale use of energy crops for CDR, especially in biomass prioritizing portfolios, can put significant pressure on food supply and biodiversity. Studies show that converting cropland to energy crops may threaten food security and violate sustainable development goals. Technical CDR options, while energy-intensive, avoid most of these land use conflicts. Sustainable afforestation and biochar can offer some biodiversity benefits if managed carefully, but the overall message is clear. Minimizing land demand is crucial for balancing climate action with ecological and social needs. In summary, the area demand for negative emissions depends heavily on the chosen technology portfolio. Biomass-based CDR can require vast land areas, risking food security and biodiversity, while technical solutions like DACCS keep land use low but need more energy. For both 1.5 degrees C and 1.0 degrees C climate targets, non-biomass portfolios can keep net area demand below 1.4% of global land. The right mix of CDR routes, integrated with renewable energy, can help us meet climate goals without overwhelming our planet's resources. Ongoing research will refine these estimates and guide sustainable policy choices.